Okay, in this one, I want to solve two eigenvalue problems. Okay, now remember that an eigenvalue problem, um, something that looks like this. I'm going to focus today, focus in this video on two examples. The first example here, and the third example. Those two examples. The first one is what underlied this pair of examples that I did for boundary value problems. I gave you um, uh, uh, two boundary value problems, and this first one had infinitely many solutions. These were when lambda was equal to 1. And it had infinitely many solutions. In particular, it had non-zero solutions. So in the language of that we now have, we say that this eigenvalue problem has eigenvalue lambda equal to 1. And eigenfunctions are going to be multiples of sine of t. Now, again, just like with eigenvectors, we just need one eigenfunction for each eigenvalue. So we're going to take as our eigenfunction sine of t. Make sense? And then we looked at this situation where lambda was equal to 2. And what we discovered is that there are no non-zero solutions. The only solution to that boundary value problem is the zero solution. And so we say that lambda equal to 2 is not an eigenvalue. It's not. Okay? We want to find all eigenvalues. So let's do that. So let's find eigenvalues and eigenfunctions for the problem, for the eigenvalue problem, x double prime plus lambda x equals 0. And x of 0 is going to be 0, and x of pi is going to be also 0. So remember, the game here is to find lambdas. We're trying to find lambdas which give rise to this boundary value problem having a non-zero solution. The game is the hunt is for lambdas, okay? We're going to break this down into cases according to the sign, the SIGN of lambda. So let's start when lambda is positive. That's maybe the best case. So if lambda is positive, then you can check that the general solution to this, the characteristic polynomial is going to have complex roots, purely imaginary complex roots. And those roots are going to look like the square root of lambda times I, plus or minus the square root of lambda times I. So the solution, the general solution to the differential equation is x of t equals a cosine square root of lambda times t plus b sine square root of lambda times t. If you don't believe it, review, because that's the important stuff there. All right? Now let's incorporate the boundary conditions to see what that might say about a and b. So let's look at the first boundary condition. If we plug in t equal to 0 into our general solution, the sine term dies, and cosine of 0 is 1. So what we're left with is just a. In other words, a is 0. If we're going to be an eigenfunction, or if we're going to satisfy that first boundary condition, then a must be 0. Cool. That's nice. Let's look at the second boundary condition, that x of pi is 0. Well, let's plug in pi. Now, let's use the fact that we already know a is 0. Let's incorporate that in. If we plug in pi, we get b sine square root of lambda times pi. Now, here's a fact that I hope you all have incorporated into your mathematical worldview. Sine of x is 0 happens precisely when x is an integer multiple of pi. Okay? So at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7,000 pi. The integer multiples of pi are where sine of x is 0. Similarly, the negative integers multiples of pi. Negative pi, negative 2 pi, negative 3 pi, etc. Think about that good old unit circle if that's mysterious to you, okay? So in particular, if we want an eigenfunction, if we want lambda to be an eigenvalue, then we need to require, because a is already 0, we need to require, so a is 0, we need b to be non-zero to be an to give rise to an eigenfunction with eigenvalue lambda. But if b is non-zero, that forces this guy, sine of square root of lambda times pi, to be 0 to satisfy the boundary condition. So we need sine of square root of pi times, square root of lambda times pi to be equal to 0. But now look at this green fact. That happens when square root of lambda times pi is an integer multiple of pi. So I'm going to write that integer as k. Now, divide both sides by pi, square both sides, and we learn that lambda is equal to k squared, where k, again, is an integer. What you're seeing here is quantization. You're seeing a kind of continuous problem giving rise to a discrete set of values, okay? And this is the phenomenon that physicists in the past used to postulate the structure of the atom with the various energy, the discrete energy levels for electrons in the atom. Anyway, that's way too interesting to talk about. What this means, the conclusion that we draw, is that lambda equal to k squared, or sorry, let me write it like this. The eigenvalues, good God, the eigenvalues for this boundary value problem, when lambda is positive, are lambda equal to k squared. And the associated eigenfunctions are, now again, we only need to take one representative for each eigenvalue. So what we're going to have is x of t, I'll just call it x of t for now, sine, now we take the square root of lambda is k times pi. Okay? Oh, sorry, times t. My bad. Times t. And this is for k, an integer. Alrighty? And in fact, we can just take positive integers, actually, because we're squaring k here. So we can take k to be 1, 2, 3, 4, etc. All right. So that takes care of when lambda is positive. Cool. How about when lambda is 0? Well, if lambda is 0, then our differential equation becomes x double prime is equal to 0. It's very silly. And the general solution here is pretty straightforward. It's x of t equals at plus b. You should check this if you don't believe it. You're going to get a repeated root in your characteristic polynomial, yada, yada, yada. You should know how to do this. Now let's look at what the boundary conditions say. The first boundary condition says that 0 is equal to x of 0. But x of 0 is simply b. Okay? So, in other words, b is 0. Cool. Second boundary condition says that 0 is equal to x of pi. But if we plug in pi and b is 0, then we get a pi. Pi is not 0, and therefore a is 0. To satisfy that second boundary condition. Ouch. That means a is 0 and b is 0, so that means that x must be 0. In other words, lambda equal to 0 is not an eigenvalue. Because the only solution to the boundary value problem is the trivial one when x is 0. Okay? Last case is when lambda is negative. Okay? Yeah, so what happens if lambda is negative? Then, yeah, let's think about the... So we get x double prime plus lambda x. I'm just rewriting the differential equation. What I'm going to do is I'm going to write... So if we write down the characteristic polynomial, that's going to be r squared plus lambda is equal to 0. Remember, lambda is negative here. So what I can do is I can subtract lambda from both sides and then take the square root of both sides. And when I take the square root of negative lambda, I get a real number. This is equal, the solutions to this are r equal to plus or minus the square root of negative lambda. Now, it's a pain in the neck to keep writing square root of negative lambda. So let's call that real number, that positive real number, let's give it a name. Let's call it maybe p. Is that okay? So r is equal to, yeah, I'll just rewrite this as plus or minus p. Okay, this is just going to make it easier for me to write things down. All right? Then what are the solution? What is the general solution to this differential equation here? It's going to be x of t equals a e to the pt plus b e to the negative pt. My roots are p and negative p. Those are real and distinct roots. And so this is what the general solution looks like. All of this is review, okay, from when we were talking about second order equations. Cool. Now let's see what the boundary conditions imply. So 0 is equal to x of 0, right? So that says that if we plug in t equal to 0, replace t with 0, we get a plus b. Meaning that a is the negative of b. Okay? So we can incorporate that in thinking about the second boundary condition, which says that, of course, 0 is equal to x of pi. Now, if we plug in pi into x of t, and we incorporate this fact that a is equal to negative b, then we learn that negative b e to the p times pi, oh my gosh, I'm going to say p pi, plus b times e to the negative p pi, that's 0. Okay? Now I'm going to add b e to the p pi to both sides, and I learned that b e to the p times pi is equal to b e to the negative p times pi. Okay? Note that b can't be 0. Because if b were 0, what would a be given this condition? It would also be 0. And what would that make x? That would make it be the 0 function. And we're hunting for non-zero solutions. So we can assume safely that b is not 0 and see what happens. If b is not 0, then that implies that e to the p pi is equal to e to the negative p pi. Now take the log of both sides. P pi is equal to negative p pi. Now divide both sides by pi. And now ask yourself, how in the world could this happen? How could p be negative p? There's only one way. Add p to both sides, divide both sides by 2, learn that p is 0. But p can't be 0. Because if p is 0, look back here. That would say that the square root of negative pi was 0. Sorry, lambda. Square root of negative lambda was 0. But that would imply that lambda is 0, but lambda is negative. Okay? What this shows is that lambda negative can never be an eigenvalue. And we did it. We solved this eigenvalue problem. For this eigenvalue problem here, this one, we found the complete set of eigenvalues and associated eigenfunctions. Here they are. The eigenvalues are when lambda is a square of an integer. So that's 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, etc. And we have the associated eigenfunctions. They're x of t equal to sine kt. Okay? All right. Let's pause there, and then we'll do another eigenvalue problem in the next one. I'll be a little bit more brief in the next one. Okay, see you then.